and 2 units, it can become much more complicated. Because why? Because you can combine different units together. So say you have unit 1, 2, 3, dot, 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 n. So you can take them pairwise, you can take them more than 2 together, and so you can have so many different types of subsystems, and soon it becomes very difficult to handle this on pen and paper, right? But what I said is that we'll give an example of such a process, and very often you need a lot more information than is available to calculate all the stream quantities. What is the mass flow rate of every stream? What is the mole fraction or mass fraction in every stream? And essentially all the unknowns, right? And still we are only on non-reactive systems. So imagine all of the above becomes even one more rung of complexity we can introduce in November when we look at or a little earlier perhaps, depending on how long we take on the purely non-reactive processes. If you add a chemical reaction to this, what happens? Now only one chemical reaction is still much easier to work. Suppose I add 2 chemical reactions to it. I mean, maybe I have unit 1, unit 2 in the diagram. One is reactor 1, reactor 2, and then I carry part of the reaction in one. Whatever is not complete, I feed it to sequentially to react unit 2. And then again something remains converted, something is unconverted. I have to account for all of those chemical reactions also. I mean, all the species that are converted and remain unconverted in addition to the mass balance. Then it becomes much more interesting actually. But anyway, currently we are excluding chemical reactions, right? So we have confined ourselves to non-reactive systems. So we looked at multiple units, non-reactive systems. Now suppose I wanted to, I said is a diagram of a flow sheet. That all we did. Now suppose I had a actual process sheet. This is actually some kind of, no, there is a distillate, this is some kind of liquid extraction process. This is a kind of liquid extraction process. So it's more complex than the simple units 1, unit 2 and 2 unit systems we did. But now what is they trying to do here? They have a mixer settler combi, a combination of mixer setters, and not only one but double, 2 of them. Combi 1, so unit 1, unit 2 put together as unit 1 prime, and similarly another mixer settler unit 2, unit 2 prime. That's a combi of mixer settler which could be composite unit 2 prime. Then you also have, that was not sufficient, because what they are trying to do, it looks from the sheet, is this fed in half organic, half water. W is water and A is what? Organic is acetone, or rather solvent plus acetone. So they fed all of that, and now they have a raffinate an extract or raffinate distillate, depending on whether it's a liquid extraction as in the mixer settler combination or in the distillation column, right? And if you take the top product from the bottom diagram of a distillation column, the product is 97% A and hardly any water, and that means they have enriched it in a lot in acetone. Now if you look at the mixer settler unit 2 prime, there is, you see raffinate 2, they say it is mostly water, and there is some impurity of M and A. And the extract, because it's a liquid extraction process, which is very common by the way in industry. It's this is thousands of processes run with mixer settler units, which are solid cum liquid separations. So extract 2 here is mostly the solvent. It's an organic solvent, and there is also some contamination of acetone water. So essentially, what they are trying to do is separate out all of the organic solvent, separate out the dissolved solute, which is acetone in this case, and have a stream which is more or less all water. That is what this process is trying to do. Now, this is a good example of a part of a process sheet of a larger industrial unit, right? This could be one subsystem of that. Now, suppose they were to ask you, suppose that it was asked, find out all the streams such as raffinate 1, extract 1, raffinate 2, extract 2, combined extract going into the distillation column, and the flow rate of product, flow rate of recovered solvent, because solvent they are recovering, that is the M, and then they are going to reuse it. So suppose they were to ask you to find all the mass or volume flow rates of each of these solvent, water at each point. How is it? How can it be done? Now that's a harder question. It's a more general question. Suppose I were to say raffinate 1, find every unknown stream. How much is raffinate 1 in volumetric flow per unit time? What composition does raffinate 1 have, etc. Like that at every point, if I have to find it, the question can be put, what all information do you need to determine the flow rate and or mass flow rate or volumetric flow rate and the composition of each of the intermediate streams? A much harder question. Normally, what we do in this type of balance, what we are doing till now is we give a problem, you draw a flow sheet, and then the information that is also given to you. Nobody asks you what information do you need if you need to find the intermediate stream. Normally, so far, we have been giving you sufficient items of information such that you can label them and then find the unknowns. But in real life problem, you will have to determine what all is required. If I need to know, let us say, what is the output extract of unit 1 prime, which is the mixer settler combination. That information may not be available. You will have to find what readings I need to take or what experiments I need to do in order to obtain information so that I can get this flow rate and I can get this composition. So as things are, the above problem is insufficient, has insufficient information to get all the component stream flow rates and composition. So you will need to find make measurements. Say you are to take samples from raffinate 1 after the mixer settler unit 1 or unit 1 prime combination, and find out उसमें कितना acetone है, उसमें कितना water है, etc. I mean, there's no one set of measurements you can. So essentially, we need to determine what the information items we need, and so that we can get what is the composition, say at extract 1. So of course, I mean, this type of questions we don't ask in a 1 hour exam. I mean, there's no point giving a question where you have to experimentally determine something. I mean, obviously that's not a that could be a lab exercise, but it can't be a minor or major, right? So what we are doing is we are confining ourselves to only 2 units so that we can get a deterministic and very sufficient information which can be digested, put in a diagram, unknowns labeled, and equations solved all within 1 hour. Because just making the sheet more and more complex, there is no end to it. As I said, this could be one small part of which is 1/100th of the total process and instrumentation diagram that chemical plants often make in details, right? And we are only interested in the process aspects of those detailed diagrams. So if I were to confine myself to just 2-unit system, say reactor separator, a very common combination, just like the mixer settler, I can have a reactor come separator. But the problem is we have not yet, we said chemical reactions are still forbidden, हम लोग treat नहीं कर रहे ना, non-reactive systems कर रहे, तो reactor का क्या मतलब है? So of course, the type of questions we will now discuss, they are more interesting when chemical reactions are taking place, and we will arrive at those sooner or later, maybe by end of October. However, you can actually do them even in the absence of chemical reactions, but they take on much greater force and utility if there are chemical reactions taking place. So normally what we do is when chemical reactions are taking place, no reaction ever goes to completion. So what we do is we take the unit 1, say the reactor, we send it to a separator, a unit 2, and now there will be some stream which comes out of the separator. It's not completely converted. The A going to say it's a unimolecular reaction. I mean, first A order, A going to B type of thing. But it's not converted completely A to B in one pass. How can you, in a small residence time, in a continuous system, at least in a batch process, if you put it long enough, maybe you can expect better conversion. But in a continuous system, if you just send it once through the reactor, small residence time, high flow rate, what do you expect? You can't expect too much conversion, right? So normally what is done is whatever goes out of unit 2, which is a separator. In this case, it's a mixer settler in series, but reactor, because it could be a reactor separator in series. So from that separator, you recycle a part of that total flow rate back to the reactor. This is there in virtually every continuous plant. It has been found that such recycle is very economical, and it leads to much higher conversion, and there's a big savings of cost, and this is there in every continuous process. So let us try an example without chemical reactions, that is somewhat harder to frame, where you have more than one unit, so 2 units, and you also have a recycle stream where part of the final output stream from unit 2 is fed back, sent back to the first unit, that is the reactor, or in this case, a non-reactor, whatever it is. So let us take a look at that today. That is our aim today. So here is such a problem where there is no reaction, but there is a physical process, which however has 2 units. Instead of a reactor separator, you have an evaporator and crystallizer. They are connected in series, and certain things are given to you. You are trying to separate crystals of potassium chromate and from its mother liquor. So this is the question, and you are asked what is the recycle ratio, how much recycle, how much mass of recycle should be there per kg of fresh feed. You're feeding in 4000 kg per hour here, so per kg how much should I recycle in order to get whatever output that is given to you? You must have 36.4% potassium chromate in the final stream, and that is what you're going to also recycle. And then also total, say there's 95%, crystallization is required, etc., etc. All of those are spelled out. Also, some more information is given what happens when the stream leaves the evaporator. And then you're of course asked how much evaporation load is required, because that is something you need to find. Kitna water hame evaporate karna hai. So he also asks you what is the feed rate that the evaporator can handle, and or ditto how much the crystallization can handle. So all of this information now you have to distill. Try in the next 10 minutes to put it into form of a diagram, right? Whatever is given in this text. So it is one more step further to what we have done till now. We have 2 units indeed, just like last class. But now we also have a feedback stream, what is called recycle. And that we have to write diagrammatically. So please try and recast all of this into the form of a diagram. And of course, you have to have the evaporator, you have to have the crystallizer, and then you have to have all the input. I mean, you have to have all the in arrows and out arrows correctly. So try and do that.
Sir,
Yeah,
sir, what does the 95% signify here?
right. The filter cake. Now, what you have to first determine is what does the filter cake contain. If the filter cake contained only crystals, then this information is nonsense, right? I mean, how can it be 95%?
Hmm.
Obviously, the filter cake not only contains the crystalline solid 95%, I mean, it not only contains the crystalline K2CrO4, it contains something else, no? What is that something else? In a crystallization process, will you only have solid? Maybe can I ask? I noticed somebody with a last name which is like one of my school friends. So I will ask. It has a long name, Tek Chandani. So may I ask Dhwani whether what I meant by this? So I had a classmate with your last name, and we used to hold the whole school to ransom in marbles. We were
Yes,
both
sir.
experts in marbles. So I mean, we would win everything. I mean, we were both. Anyway, so you see, the question is, what is the meaning of 95%? So my counter question to that was that information has no meaning if solid K2CrO4 crystals was the only component. Obviously, it's not the only component. So my question to you, Dhvani, is other than the solid crystals, what else could be there in this? Is the sound of my voice coming to you, ma'am?
Yes, sir.
Nice. No,
Yes, sir.
no.
Yes,
I,
I'm just.
I just had to do this since your name's Dhwani. So anyway, that's just a parody on your name. But you understood my question, Dhwani ji?
Yes, sir. I just could I
Think on it.
get a couple of minutes just. Yeah.
Why not? Wonderful. Very, very nice. So your namesake and me, we were super marksmen when it came to marbles. And as you know, between us, it was like Nadal and Djokovic. Sometimes one wins, the other wins. But you play all of these things even in pairs. So when we joined forces, we were like a very formidable doubles combination. I wonder if any of you ever indulged in these type of activities. I think it's out of vogue in today's generation. And then the marbles used to be taken away by the school, though. I mean, it's not. I mean, not that there is anything wrong in playing marbles, but the school never encouraged, right? Convent schools are like that. So to reframe the question, what else could be there in that stream along with the solid or crystal, along with the crystal? Obviously, you have to interpret it right. Otherwise, how will you draw the diagram?
That is the rest 5% mother liquor only.
Correct. So what he's saying is this filter cake has two components: the K2CrO4 crystal, very clear in the line above, and a solution that contains so much percentage by weight of K2CrO4. So in other words, you cannot separate the solid completely. It will have a liquid mother liquor from which you got the crystal in the first place, right? So it is a two-phase solution, and it also contains water, K2Ci and K2CrO4. And how much percentage by weight, that is also given to you. But if you take the total mass of this two of all of these components, the crystals plus the mother liquor contain, I mean, shouldn't call it mother liquor. I mean, the liquor at the end with which this thing is in equilibrium, which is itself a two component system containing water and K2CrO4. 95% of that is solid. That is what this piece of information is telling us. And then if you it also tells you what is the recycle stream. The composition of the recycle stream is given to you. That it is logical that the composition of the recycle stream equals the composition of the liquid part of the output, because that itself you're recycling, and it is the same as 36.4%. Otherwise, you can make that composition different, but it doesn't make any sense, right? I mean, whatever is the mother liquor or the liquor at the end of that, part of that you are recycling. That is Casse stream R. So when he says the recycle ratio in italics, mass of recycle, he means the mass of the stream or mass per unit time of the stream capital R, which you are recycling, and per mass per unit time of the fresh feed, which is the output input to the evaporator, not the combined input, the fresh input, not the input. Fresh feed means what you are not uncombined with the recycle stream before the recycle stream gets mixed with the fresh feed, right? And then gives you a combined feed. So fresh feed is the what should I say, the stream before the combined, before it joins with the recycle stream at that mixing point. So that's what is meant by fresh stream, which you can call F or M dot, whatever. I mean, whether then you have to give subscripts. Huh? I mean, so all I want to know is, if I were to do an overall balance on this system, that is, put all the evaporator and crystallizer together, how many streams, according to you, are going to intersect that combined unit 1, unit 2 combo? Of course, fresh feed is going in, but that is given to you 4,500 kilograms per hour. Isn't it? The fresh feed is you can take it as a basis. वो तो दे रखा है ना सबसे first line. That is joined by the cycle stream, and its composition is given to you, and the combined feed you do not know. This combined feed is what goes into the evaporator.
So first we have the fresh feed, and
Fresh feed,
then,
very good.
Yeah, then we would have the water that is being evaporated out from the evaporator, that is going out of the system.
Very good. Give a symbol to it, say capital Q, or if you want M dot, then give it subscript. Very good. What else?
And then from through the crystallizer end, we would have the recycle stream coming out of. No, that won't come out of the system.
No, that will
and
not.
And then we would have then we would have the filter cake.
Right. So how many?
Yeah, so three.
Are you sure? Think again. No. Something is missing.
Sir?
Think again. Others
so for the evaporator.
Evaporator का water load तो है, so Q subscript W or M dot whatever 1 2 3 4 however you label it, I don't know. So evaporator तो some water load तो QW तो होगा ही होगा. So that is correct. You are right there. And fresh feed is also there, F. And there is a combined feed F subscript C. But that F subscript C doesn't come in the overall balance. So now I ask you, how many total quantities will be there in the overall balance? You told me 3, but I said think again.
So only 2, I guess.
I thought you were asking about the number of streams that would intersect the combined evaporator crystallizer system.
Yes, that is also correct. It will still be the same answer, because my overall mass balance is on the combined system. So you can rephrase my question like you have done. So somebody said 3, somebody said 2. Now I mean up 1 2 3 4 5 up to the, I mean, it is after all an integer number. So but I didn't agree with what you just now said. So think again. Because the next logical question is, once you get the number right, what are they? What are those streams? But first you have to get the number right.
So we need four quantities to be able to do the complete balance.
I think you need 4. There are 4 streams there, the overall balance. Definitely, because you have the fresh feed. Recycle, as you correctly said, doesn't come in because it comes within that overall balance. So you don't need to worry about that. You already told me there is an evaporative load, Q subscript W or whatever M dot you are going to label it. Then you have the combination of the crystal and the mother liquor and the liquor that is in equilibrium with it. So those are 2 different things. No, one is pure solid, K2CrO4, but the other is a mixture of water and 36.4% K2CrO4. So वो भी तो overall stream होगा. So there will be definitely 4 intersecting either input or output to this overall unit that you enclose by a rectangular dotted line or dash line. Indeed, there are 4, of which you only know the fresh feed. So all the other 3 are unknowns. So essentially, it looks as follows. So if I were to draw a boundary overall, you will get the 4500. You will get the QH2O there going up. You will get the solid crystals in the filter cake, and you will also get the whatever is the total mass of the K2CrO4 solution. So 4 variables. I mean 4 quantities, of which only one is known. It still doesn't label the variables, okay? That you still have to do. Whatever I call the stream which is recycled, which goes 36.4, which goes to the 4001, that I call R, but you can call it M dot 3, 4, 1, 2, whatever you want to call. So you have to still label the variables. But yes, you're right, QH2O is one variable. Mass of the filter cake, whatever you are going to call it, solid, subscript SMS is one variable. And then M solution is another variable, but that contains both K2CrO4 and water. However, what is given to you is that of the total mass, 95% of that is crystal. Solid of this cake containing solid liquid. So that information now you have to see how to use it.
So can we use the mass balance twice?
Yeah, why not? You can use the mass balance twice, but
Like once after the evaporator and then after crystallizer?
yeah, you can, of course. What I suggest, instead of doing mass balance twice, means एक overall balance or एक component balance, either on water or on K2CrO4, you will have to anyway use. Again, we said that only 2 of them are independent, right? Number of components are 2, so 2 balances will be independent. So you have to supplement it anyway with either a water balance or a K2CrO4 balance in the overall sense also, I'm saying. But that still doesn't utilize the information which is on the rightmost side of this diagram. उसको आप recast करिए ना पहले. I mean, that is an additional information, no? He has given you something 95%, 5%, something, etc. No? Right. I mean, of course, it does require some thinking, I mean, but you have to separate. You see, you correctly told me that there are 2 variables. The mass of the crystals, let us call it M subscript C, and the mass of the solution which comes out of the crystallizer and filter, right? तो वो दोनों 2 वेरिएबल्स है ना, तो उनको भी तो रिलेट करिए आप. Okay, let's put it another way. Don't look at all the three components: solid, crystals, and then the the liquor solution, the output solution containing K2CrO4 and water. But you can definitely, sorry, there's the, you can definitely look at the total mass that comes out of the crystallizer and filter, and of that, how much is the solution or how much is the solid. Solution is only 5%. So why not? Won't that give me an additional relationship between the total mass, which is anyway there in your overall balance, which is, you correctly told me, is the mass of the crystals plus mass of the solution, and mass of the solution is only 5%. So I have one more equation in addition. So the overall mass balance has three variables, three unknowns: the water load, the mass of the crystals, and the solution, or the mass per hour of solution, and mass per hour of water, and mass per hour of crystals. Now you will form an equation because you know that the solution mass is only 5%. Of course, that still doesn't solve it. I still need to get another equation. So we still have to think, but at least write that equation. See, we are still doing overall balance. Okay, हम लोगों ने कभी भी अभी हम लोग evaporator पे पहुंचे नहीं है separately, nor crystallizer separately. And exactly this we can do as separate units, but that's what I meant. If there were multiple units, then you need to combine units, and you can do them in so many different ways. Anyway, here we don't have that problem because we have only 2-unit system, and there is no reaction also. But still we have three unknowns, and at most right now, even if you get that other equation correctly, you have only 2 equations. So where is the third equation going to come from? Is my question clear? Even if you could use that information of 95% of the total mass of the liquor plus crystals being only 95%, one being 95 and the solution being 5%, which is some kind of ratio, you can say, it will still leave one unknown, and because we have 3 unknowns in that overall mass balance. So along with the overall balance, this will only give me one more equation. Where is the next equation going to come from? Still looking at overall balances. We haven't looked at any balances on individual units yet. I mean, if we do that, that will give us new unknowns, like QH2O will be an unknown if we look at the evaporator, right? And then we have to worry about the recycle stream also, because R is also being fed into the evaporator. So that will make it even worse. So we are still looking at the overall boundary. What is the fresh feed boundary, which contains the recycle stream and contains the output of the crystallizer filter. इतना ही हम कर रहे हैं अभी, which I called overall balance, right? We always called.
So for the filter cake, the mass of K2CrO4, can we write it this way? 1 into 0.95 plus 0.364 into 0.05.
Not really, no. It's not what the, I don't think so. Because if you read what is written in the problem statement, which is sort of summarized here in the rightmost part of this diagram, that's not the overall balance, is all I'm saying. I mean, go back to the problem statement. It's very clear that the crystals are only 95% of the total weight of the filter cake, and the filter cake itself consists of the solid and the liquid part. So for the moment, don't divide the liquid into K2CrO4 and water. In the overall balance, why should I do that? So there's no point in taking the 36% and combining overall with K2CrO4. First do the overall balance. I don't know. I mean, you can do like you're saying, but then you're mixing up things. I mean, we are trying to still follow the procedure we laid out, you know. I mean, 1, 2, 3, 4 करके वो पूरा lecture हमने उस पर बिताया ना, तो अब if we violate it, then the whole thing is. I mean, of course, you can do it in any order and any way you want, and our students are good at doing it. But then we are trying to see what maximum we can get from the overall boundary. So what you told me is not what this problem statement tells, and nor is it what is summarized here on the rightmost part. Crystals in the bracket, crystals constitute 95%. No, is not what you told. Okay. Anyway, it looks like we definitely have to discuss.
So the mass.
Yeah.
The mass of the crystals should be 1500, right? Because initially the K2Cr2O4 that is going in is 33% of the 4500 kilogram per hour
No, not necessarily.
solution that we're putting in.
It would be 1500, provided there were, nothing coming. There was that 0.3636 times the mass of the solution were negligible, but it's not negligible. No, you do not know what is the mass of the solution in that liquor phase, which is in equilibrium with the solid. You cannot take that zero. If you could take that zero, then only you are right. But since here the information is given to you, you can't take that zero. So you'll have to find. So it will be something little less than 1500, according to me. You understand? It won't be 1500. It will be 1500 only if this, instead of 95%, if it was 100. Because by chance, it may not be too far lower than 1500. So in your case, maybe it comes to 1400. It may not make too much difference, but that's because it's 95%. Suppose it's on 95% or 80%, then the errors will start mounting, you know. So the actual value that you will get will be lower, according to me, lower than 1500 for the crystals per hour. So you have to find out exactly how much that is lower. In this particular example, it may not be lower by too much, but you have been given, you cannot assume it 1500. You got my point. Anyway, it looks like we have to continue this. It is we are still some way from. We are still only looking at the overall balance, and we still have to look at components or at least units separately. We haven't done that yet, and so we will continue on this on on Wednesday and complete it. And then later, once we do all of this week, we need to worry about adding reactions. And of course, we are not going to directly add reactions to this recycled system, but ultimately we will want to reach there, right? That's what we would want to do by first week of November. Okay. And then we can go to energy balance. So first mass balance without reaction, what we are doing now, more than one unit, then recycle with more than one unit. Then now we add chemical reactions without recycle. We do multiple reactions, and then we add this reaction with recycle. So this much we want to do. And then we are ready with that mass balance part complete. That's all we can have time for. Then we will go to energy balance. And then we will see, let's see how long it takes us. Okay, so on this, let's continue on Wednesday. Thank you.